Hi everyone. I'm going to get started in a few minutes. I've been. We're recording, by the way, Ben. And I'm going to get started in like 2 minutes. Can you hear me, Ben?
Yeah, Professor. Yeah, I'm here you now.
Thank you.
Yeah, I'm here you now. I'm here you. Professor, can I asking for the
Yeah, go ahead.
can I also can you open for the homework 11? Cause on the yesterday I just haven't like reviewing a lot for the any classes, so just having the time to finish. So today just trying
Sure.
to finish it.
Yeah, let me open that right now. If it will ever open.
Wait, I think it's no people. It's just coming. Oh, okay. Saw it now.
Oh, why it's not open? Why do you not want to open? Um, I don't know why it doesn't want to open. I can open it on my other computer.
Okay.
Anyway, hi Anthony. Oh, we are recording, you guys, so if you don't stay the whole time, it'll be posted later. And you'll be able to watch it. Bob. So you said homework.
So the homework 11. Homework 11.
It let me open it here. So I'll open it till Thursday, I guess. Should be open till Thursday now, Ben.
Oh, to the Thursday, right?
Yeah, should be. I opened it on my other computer.
Okay.
All right. So, hey, everybody. I'm sure people are going to be joining, but I'm going to go over today the physics summer 22 solution guide, and I'll go through, I'll do an overview of the problems too. So our final is going to essentially cover 4 topics. Chapter 14, which is fluids, which is Bernoulli's, I'm probably going to spell it wrong. Bernoulli's equation. From chapter 15, we have physical pendulums and oscillation equation. And then our last thing is Kepler orbits and gravity. And so what you can expect is that we're going to have 4 questions, one on each of those topics. And you'll have your 2 hours, you'll have your 2 cheat sheets. It'll be fairly close to the things I ask on the practice final. So just make sure you know these 4 topics, and if it's something that's not on here, it won't be on there. For instance, we talked about Pascal's equation and we talked about buoyancy with Archimedes. Those won't be on the final. Sorry, got a bit of a cough today. So what I'm going to do is, as we go through here, I'm going to cover them kind of in orbit or in order. And if you have any questions, just let me know. And then at the end, if you have any homework questions that you want to ask, you can do that too. So we're going to start with Kepler orbits. And Kepler's first law said that planets orbit in ellipses, which means if we have an ellipse, we can divide it up in 2. The sun would be at 1 focus, and I should actually draw that a little bit larger. So the planets go around the sun in what are called ellipses, and the sun is at 1, what we call a focus. So this distance and this distance are little a. They stand for the semi-major axis. This distance from the sun to the center is E times a, where E is the eccentricity. This distance right here is known as the perihelion distance, and then this whole distance is known as the aphelion distance. And what Kepler said was, if you added RA and RP, these 2 distances, this distance and this whole distance together, you get 2 times the semi-major axis. And then if you add RP and EA, that is E times A. Those are 2 numbers. You get A, and if you added RA would be A plus E. So what we can do is we can ask, given 2 of these, if I gave you RA and RP, you could find A, and then you could find E. If I gave you E and A, you could find RP or RA. So given any 2, you can find the other values. Kepler's second law that Newton said was actually angular momentum says that when we're at RP or RA, we have a velocity at both of those. And the velocity times the radius is a constant. And that's because of conservation of angular momentum. The third law is that T squared is equal to A cubed. In Kepler's version, this is in Earth years, and this is in what are called AU. 1 AU is 1.5 times 10 to the 11th meters. It's the distance from the Earth to the sun. So if you're doing Kepler's version of the period law, this is true. If you're doing Newton's version, then T is in seconds. And talk more about this, but this is 4 pi squared over the gravitational constant times whatever you're orbiting. So if we're orbiting the sun, this is the mass of the sun. If we're orbiting the Earth, it's the mass of the Earth, where G is 6.67 times 10 to the minus 11. It's a gravity constant. A is the semi-major axis. T is the period. Now we'll probably end up using Kepler's version, so you'll be in Earth years and you'll be in AU. But as we go and look at this, so all of these equations are here for you. If we're not going around the sun, we have to have T in seconds. We have to have A in meters. So you just have to switch them if they weren't in those things. So here we have Saturn, and I've given them the mass and the radius of Saturn. And we want to place a satellite in orbit so that the period is 20 hours, otherwise known as 72,000 seconds. You're given the eccentricity and you're given the orbital velocity at perihelion. So this is just making sure that people know your equations that matter. First thing we can ask is, since we've been given the eccentricity here and we know the period, we can find from the period, we can find A. And then since we have A and E, we'll be able to find a whole bunch of other things. So our first step here is we know the period, we want to find A. T is related to A in this case. We have to use Newton's version here because, and I'll write these, because we know G is 6.67 times 10 to the minus 11. The mass of Saturn was given in the problem as 5.683 times 10 to the 26. And again, everyone, this is being recorded, so you'll be able to watch this later. It usually takes about an hour to compile once we stop recording. So knowing this, we can compute A. And one thing to note, so if I move everything over, I get T squared G mass of Saturn over 4 pi squared. We're trying to find A first, the semi-major axis. A is the semi-major axis. And to get rid of a third, so you've probably gotten used to doing like A squared is equal to B, and then you take the square root. If you're not used to getting rid of thirds, you can just multiply both sides by a third. So you can raise this whole thing to the third power. And that gets rid of this third root. We said the T was 72,000. So you can put this all in your calculator. 72,000 squared, 6.67 times 10 to the minus 11, 5.683 times 10 to the 26, and then all over 4 pi squared, and raise this to the 1/3. Now, if you do all that, which is all done here, this is another way of writing to the 1/3 power. We find that our A is 1.707 times 10 to the 8th. Okay. Just keep that in mind. Now we could turn that into AU. We're not going to because we're around Saturn in this case. But if it was an AU, we could leave it in AU. The next thing we want to find is we want to find RP and RA. And since we know A and we know E here is 1 or 0.05, we can find RP and we can find RA. Just plugging in those numbers, 1 minus 0.05 times 1.707 times 10 to the 8th, 1 plus 0.05 times 1.707 times 10 to the 8th, and you get these are your RA and RP. So again, once you have A, RA is equal to A plus EA. And here our E was 0.05. Our A, which we just found, was 1.707 times 10 to the 8th meters. E has no units. So we could pull an A out, and this is just 1 plus E. We can find the perihelion distance, because the perihelion distance is A minus EA. So it's A1 minus E. Now remember, what these are is if the sun is sitting here, this nearest to the sun is our RP. This distance furthest from the sun is RA. since this is EA, and this is A, and this side is A. So RA is A plus EA. RP is A minus EA is RP. So if I took A and I subtracted off EA, I would get RP. Yeah, this will be available to you though, Ben, just so you know. And it's all on that solution guide here. Okay. All right. So once we have this, if we go back to the second law says we now have RP and RA. And if we read the problem, we were told that at perihelion, the velocity was 1500. So VP times RP is equal to VA times RA. And we want to find VA. We know VP is 15,000. And we just found that RA and RP were 1.622. And 1.622 times 10 to the 8th times 10 to the 8th. So if we're trying to find VA, divide both sides by RA. And you get the VP times RP over RA. This is 15,000. But then here, we can cancel the 10 to the 8th. We don't have to put those 10 to the 8th in because top and bottom both have them. And so I get 15,000 times 1.622 over 1.792. And that will give me 13,700 meters per second, slightly less. The big idea here is that as objects go around, when you're close to the sun, as you go around in orbit, when you're close to the sun, what we call VP, versus when you're furthest away from the sun, VA. VA is much less usually than VP. Well, it's always less, but usually it's much less if the eccentricity is high. Another thing to remember, and it's not going to be on the test, but E is 0 for a circle. And the reason for that is if we go back and look at your ellipse, right, where we have this distance and this distance from the sun to the center, if E were 0, the sun would be sitting right at the center and RA and RP would be the same. If E is greater than 0, but less than 1, you get what is called an ellipse. The bigger or closer it is to 1, the more stretched out your orbit is. When E is 1, you get a parabola, and we don't need to worry about that because that is not closed. And greater than 1 is a hyperbola, which is just a parabola that's a lot steeper. So this satellite being at an eccentricity of 0.05, it's basically in a circular orbit. It's very close to a circular orbit. Now, the final thing I asked on this, and I probably will not ask it on the final, I may, because you should know this from fluids. The density of anything is its mass over its volume. If we assume it's uniform and a sphere, so for a sphere, the volume is 4/3 pi r cubed. Now, if we plug in the mass of Saturn, 5.68, 3 times 10 to the 26 kilograms, and we plug in the volume, 4/3 pi, the radius was given as 6.03 times 10 to the 7th, and you cube that. What you'll see here is that this density ends up being somewhere around 600 kilograms per meter cubed. For fluids, you need to remember that fluids, water has a density of 1,000. And anything with a density less than water floats. So the reason why you float in the swimming pool is your body is actually slightly less. One of the really weird things about Saturn is if you compute its density, you'll find it's 619. That means Saturn would actually float in the ocean of Earth if somehow it could float on Earth. It's just weird. Saturn's less dense than water, significantly less dense. So the last thing I want to say is if, which we probably will have on the final, if your RA and RP are given in AUs, so if they're in AU, for instance, Earth, the distance from the sun to the Earth, the average distance or semi-major axis is 1 AU. For Mercury, it's like a third. So let's say Mercury's got basically RP is 0.3 AUs. And let's say, I don't remember what Mercury's RA is, but let's say it's 0.4 AU. If I told you that, you could tell me the eccentricity and you could tell me the semi-major axis, because RP plus RA is 2A. So if I wanted A, I would just divide both sides by 2. And I could leave it in AU. So here I would get 0.3 plus 0.4 over 2, which would be 0.7. So 0.35 AU is our semi-major axis. In Kepler's version, T squared is A cubed. If T is in Earth years and A is in AU, you don't have to worry about that 4 pi squared over GM. So if you're asked for Earth years, right, what you would get is find the period in Earth years would be A to the 3/2 power, or 0.35 to the 3/2 power. So Mercury would go around the sun in 0.2 Earth years. Okay. So here's the thing. You don't need to use meters or seconds if you're rotating around the sun. So if I give you a problem like, I don't know, an asteroid going around the sun, and I give you RA and RP in AU, or I ask for them in AU, you don't need to put it in meters or seconds. It makes it a lot easier because then we don't have these huge gross numbers. But the equations are still the same. All these equations are still the same, except this is equal to 1 if T is in Earth years and A is in AU. I'm not going to do that conversion for you, but it actually does work if you do the conversion from Earth years, seconds per Earth year per period, and meters per AU per A. Anyway, if anyone has any questions, you can throw them in the chat for a minute, and otherwise we'll move on. I think Kepler's equations are pretty straightforward. The first law is orbit and ellipses with the sun at one focus. The second law, and it gives us these 3 equations. Second law is equal area, equal time. And that tells us that the velocity times the radius at any point in the orbit is a constant. So we set the velocity and radius at aphelion equal to the velocity or radius at perihelion. And the final one is that the period squared is equal to A cubed. In Kepler's version, period is in Earth years, A is in AU. In Newton's version, T is in seconds, A is in meters, and G is 6.67 times 10 to the minus 11, and M is whatever you're going around as mass. All righty. We're ready to move on. And by the way, this was chapter 13. We'll come back to gravity a little bit at the very end. But chapter 13, we're going to talk about Bernoulli's equation. And what Bernoulli's equation does is it tells you that the total pressure consists of 3 different pressures. It consists of a static pressure, it consists of a gravitational pressure, which is the density. So this is pressure. This is the density of your fluid, and obviously the height, and the density times the velocity. So this is the velocity. We call these the static pressure, the gravitational pressure, and the kinetic pressure. Bernoulli's tells us that the pressure at any point is equal, and this is the total pressure, is equal to the total pressure at B. So we can choose 2 points, and we can write that the pressure at A and the density times the height at A times the pressure times the velocity squared at A is equal to the static pressure, the density, the height at B, plus the velocity squared over B. The second thing we have is the continuity equation. What the continuity equation says is if you pass through a pipe that changes in area, okay, the cross-sectional area, this is pi r squared, this is pi r squared, obviously the area falls. If we take the velocity times the area, we get what is called the volume flow rate. This is meters per second, this is meters squared, so we get meters cubed per second. And everywhere, the volume flow rate is equal or constant. So it's called the continuity equation. It's a consequence of the fact that water is incompressible. Whatever comes into a pipe has to leave. And you know this if you've ever put your thumb over like a hose and closed a little bit of it off and it sprays much faster. That's because you're blocking off some of the area, and that makes more, or the mass has to flow faster because the same amount has to leave that's coming in. And if it has a smaller opening, then more of it has to go through at the same time. How we use this is we usually will write maybe VA is A, B, VB over AA, or vice versa, to eliminate one of our velocities, is usually what we do. We usually don't know, we may not know either of the velocities, but we can eliminate one of our unknowns by using continuity. One other thing that you need to remember is the static pressure outside. If it's open to the air, then the outside air is 101,325 pascals. So if something's open, you open up a jar, you open up a soda bottle, right? So let's say we have a soda bottle that you open to the air. You take the cap off. The pressure in here might be something, but the pressure here where it's open is air. So the pressure outside is 101,325. Anywhere something's open to the air, it has pressure of the air, 101,325. That's just a fact. So this is what you need to know. We're going to go through a problem, and you'll see how this all works. Hoping you already know how it all works. But so we did this problem before, except we did it where it was flowing out. In this problem, we have water coming into a tank that's open at the top, and I told you it has 1 atmosphere. At the bottom, the height is 0. At the top of the water, it's 4 meters. It comes in at pressure PC, but since the top is open to the atmosphere, this is 1 atm. 1 atm is 101,325. What we want to know is we're told the velocity at this point. We need to find the pressure is what we're going to try to find, and we're going to find the velocity. We know the cross-sectional areas at A and C. I called it A and C. I don't know why I didn't call it A and B. I think this had a different B on it that I took out. But anyway, so we know the cross-sectional area of this pipe, and we know the cross-sectional area at A. We've been given those. We know the velocity at A. We know the density of the water, gravity, all that good stuff. So the first step to do this is you write your variables. So I'm going to, just for clarity. So we have this water up here at A that's open, and this at the bottom. And what we're going to write is we write PA plus rho G HA plus rho VA squared over 2 PB plus rho GHB plus rho VB squared over 2. That's the first thing you write. That's just Bernoulli's equation. The next thing you do is figure out, do I know any of these? Well, I know this is open to air. So I know that PA is 101,325 pascals. I know the density of the water is 1,000 because it's water. I gave that to you. But I know that the height at A was 4 meters. If I look 4 meters. I know the velocity at A, if I read the question, was 0.11 meters per second. So I know VA, rho, HA, PA. I'm sorry, I called this GB. I keep trying to do that. These are actually P's or C, right? By the way it's labeled. So the pressure at C, I don't know. The height at C, I do know is 0. And the velocity at C, I don't know. The last thing that I do know is I know that the cross-sectional area at A and C were 30.3 and 6.07 meters squared. Okay, and so that's your first step, is just to write down Bernoulli's equation. Just write it symbolically. Literally, you will write just this. And then go through each one and write down, if you know what it is, what it is. So you can see that that's what I wanted them to do here. Okay. Then we want to find the velocity at C. And looking at this, if we tried to find it with this equation, we don't know PC, so we can't use Bernoulli's equation. But what we can use is VA times AA is VC times AC, the continuity equation. So VC is AA times VA over AC, or 30.3 over 6.07 times 0.11. And that, if you look at it, is 0.549 meters per second. So now I know that this is 0.549 meters per second. And the only thing left to find is going to be PC, right? The pressure that it comes in at. So if I rewrite this, I have PA plus rho G HA plus rho VA squared over 2 is equal to PC plus rho GHC plus rho VC squared over 2. That's just Bernoulli's equation. But I said this was 0, and I need to move this guy over. So I'm going to flip around the whole equation. I get PA plus rho G. All I've done is I'm just changing sides. VA squared over 2 minus rho VC squared over 2. And so what I get is 101,325, 1,000, the density, times G, 9.8, times HA was 4, plus 1,000 over 2 times, what was it, 0.11 squared, minus 1,000 times 549, I think was what we found, squared. And if I do all of this, we do all of this. I find that it has a pressure of 143.80. 143.80 pascals. The conversion between atmospheres and pascals is 1 ATM is 101.325 pascals. So if I multiply this, I get around 1.4. The conversion between PSI, like your car tires or your bike tires, over that is that. So I'm about, I don't know, probably like 20 PSI, I think. I asked for atmospheres here, just to make sure you know how to convert between the two. But sometimes they'll give you atmospheres. 1 atmosphere is 101.325. If you had 1 million pascals, that would be about 10 atmospheres, right? And 1 million pascals would be about 147 PSI. So just make sure you know how to convert. The last question is actually the hardest of these because you have to understand something. In the last question, I have that the pressure is coming in, and I want to know the maximum height that this water is going to reach. So I want to know what H is if the pressure at C is 120 PSI. First of all, you need to change this into pascals. There are 14.7 PSI for every 101.325 pascals. So you have to change that pressure into pascals. Second, you need to know that when the water has reached a maximum height, the water isn't flowing in anymore. The pressure down here is holding the height. So if I write PA plus rho GHA plus rho VA squared over 2, you just always write Bernoulli's equation. And I keep doing that. I'm sorry, you guys. Keep wanting to. Now, first of all, we know that H down here is going to be 0 still, so that'll go away. I know that this is 120 PSI, although I need to change it to pascals. I know this is 101.325 still. But here's the trick. When the water is at max height, no velocity. So there's no velocity, no water's coming in, no water's going up or down at A, no water's coming in or leaving at C, which means that this and this go away. What I get is I get PA plus rho GHA is equal to PC. If we wanted to convert that, 120 divided by 14.7 times 101.325. This is 827.142 pascals. I want to find HA. So first of all, rho G HA is PC minus PA. Divide both sides by rho G. So now what you see is, I'm going to do it right here. H at A is PC, which was 827.142 minus PA 101.325. The density of water is 1,000, and this is 9.8. So if I do that, 1,000, 8, I get a height of 74 meters. Now, looking at this, you start with Bernoulli's equation again. And we know at maximum, when the water reaches its maximum, no VA, no VC. You have to be able to understand that. I'll probably lay that out in a problem if I asked you and say, look, let me see if I did that. Yeah. So I tell you right here in bold, if I write something in bold on a test, that means it's important. So I told them At maximum height, assume the velocity at A and C becomes 0, and the maximum pressure is 120 psi. So they needed to find HA, assuming BA and BC were 0, and change the pressure at C into pascals. You have to be in pascals. Pascals are the SI units. And if you're not an SI, you can't measure meters or gravity or any of that stuff. Okay. So hopefully that all makes sense. And it's pretty straightforward. I'm going to come back to, or no, I'm going to do this right now. I want to do oscillations. I'll come back to the pendulum. But oscillations, now we've talked about this a few times, but in oscillations, you know the equation. You know that the equation is x of t, so the position at any time. One simple view of an oscillating system is a block on a spring. And that block would normally be at 0 if you didn't push it or pull it. But as soon as you push it in to some distance, negative a, or as soon as you pull it out to some distance, a, and let it go, it's going to go back and forth and back and forth and back and forth on that. So, oscillating. I don't know if this will let me, but so if I were to push this in, say, I don't know, I'm going to push it in 1 meter. When I let this thing go, it's going to slide back and forth between 1 meter and 1 meter. So if I push it in 1 meter and let it go, you can see that it goes between 1 meter and 1 meter. Don't worry about the force on it. If I stop this, okay, if I pushed it in, say 0.5, it's going to go back and forth between 0.5 and 5. If I pull it out 0.5, it's going to go back and forth between 0.5 and 0.5. So we could measure this thing as a cosine wave. And what this would look like if you measured it as a cosine wave. So instead of doing it that way, let's imagine it's up and down. So here's our 0, here's our A, here's our negative A, and our block is on our spring. And we pulled it up to A and then released it. It's going to start at A, going to come back down to negative A, and go over and over and over. This is a cosine wave. This is a cosine. Okay. So we know that our maximum amplitude is cosine times omega t, where omega is something called an angular frequency. And then we have this phase constant that we'll talk about in a minute. So in oscillations, you have this equation is known. Okay. If I want the velocity, this will tell you the position at any time. If I want to know the velocity, I take the time derivative of that. Time derivative of this only depends on t. Omega comes out and the cosine becomes a sine with a negative sign. Phi is a constant. This is phi, our phase. The acceleration is the time derivative of this. So I know these equations. And then I also know that when this part of this argument is 1, then V max is A omega. And I take the absolute value. And A max, the maximum acceleration, is A omega squared. If I know the mass of the block, then I know the force, the maximum force, is just M times A max. So it'd be M times A omega squared. So what this boils down to is you need to be able to figure out what is the amplitude, what is omega, and what is phi. The problem is that our block and spring that's just a metaphorical representation. I guess not metaphorical, but it's a simplified physical situation that could represent anything that has a period. So anything that returns in a cycle back to what it initially, its initial position or state. So how you do this is A, which is the amplitude. You'll either be told what the amplitude is, or if you're told that it travels, so remember my block that I just showed you where it went from -1 to 1 around 0, the total displacement, delta x, is double the amplitude. This is A and this is A. So if I take this divided by 2, if I'm given the total displacement, divided by 2, and that's your amplitude. If I'm given the amplitude, it's just the amplitude. Now, omega, you have 3 different ways of finding omega. So you may not remember, but the period is 2 pi over omega. So if you're told the time of one cycle, then omega is 2 pi over t. Or omega is the square root of k over m, where k is the spring constant and m is the mass. Or if you're given a frequency in hertz, 2 pi times the frequency. So depending on what you're given, if you're given the time or the frequency or k and m, you'll find omega there. And then finally, phi. So this is a cosine wave that starts at A when time is 0. It's at A, right? What if instead I wanted an upside down cosine wave? So what if instead of starting at A, I wanted to start when t was 0 at -A? In that case, phi would be pi. And the reason why, it would be 0. If I look at this and I let t be 0, this term dies at t is equal to 0, and I will get a cosine of phi. In order for at time 0 x to equal a, phi here would have to be 0 or 2 pi. Otherwise, you wouldn't get, when phi is 0, cosine of 0 is 1. You're in radians. Cosine of pi, in radians is -1. So if I want to start at t is equal to 0 at -a, I need to choose phi to be pi. And the last thing is, I could actually start at 0. So if x is 0, when t is equal to 0, phi would have to be pi half. Cosine of pi half is 0 in radians. Actually, cosine of -pi half is as well, cosine of 3/2 pi, etc., etc. But we're just going to choose pi half. So the only ones I need you to know is for phi, find x when t is equal to 0. You'll be told the system starts at A, or the system starts at 0, or the system starts at -A. And phi is either 0, pi half, or pi. That's all you have to remember. So this right here is your first step. You need to find A, you need to find omega, and you need to find phi. Plug them into your equation here and here, and you're done. That's all there really is to oscillations. So let's look at this for the human eye. If I look at a human eye, okay, the eye is 29 hertz. Okay, shake your head, your vision blurs. I also know the mass, and this should be kilograms, by the way. I believe I fixed it. And you're told the maximum displacement. So displacement is your delta x. Okay, so remember, we want to find A, we want to find omega, and we want to find phi. So when I look at this, I need to find omega first. The frequency, which is equal to 1 over t, is always in hertz. That means 1 over seconds. So in this case, where I've been given a frequency, it's 2 pi f. 2 pi times 60, or 29, I'm sorry, gives me 2 pi times 182.2 rad per second. That is the units. A, because I was given a maximum displacement, 0.0075, this is 0.00175 divided by 2, which is 0.00175 divided by 2 is 8.75 to the 4th meters. That is my A. And then finally, we're going to begin the motion of the eye when x is 0 at t is 0. When t is 0, the beginning, x is 0. If that's the case, you know that phi is pi half. Okay. So what I have is I have x of t is a cosine omega t plus phi. This is my equation. A is 0.000875 cosine of 182.2 t plus pi half. Remember, your calculator needs to be in radians. That is my equation. So when I look, I found omega because I was, well, I found omega because I was given the frequency. I found A because I knew the maximum displacement. And I found the phase angle because I knew at time 0, x was 0. I put all those in, and I will usually ask you for the equation with your constants for x, b, and a. I know that seems simple, but you wouldn't believe how many people don't know how to write the velocity and the acceleration, or realize that they are essentially just negative a omega sine and negative a omega squared sine. So this is a cosine omega t plus b, a omega sine omega t plus b, a omega squared cosine omega t plus b. Now maximum is this part, the non-cosine part of the acceleration. So the maximum acceleration is omega squared times a, or 29 meters per second squared. This should be squared. Now, the maximum force is Ka, or m omega squared a. And the reason why those two things are the same, so the force on a block, or a restoring force, is negative K times x. But our maximum x, okay, so x maximum is your amplitude. So your force, if you take the absolute value of your maximum force, should be K and A. Omega is the square root of K over M. If I square both sides, I get omega squared is K over M, and therefore K is M omega squared. So another way I could write the maximum force would be M omega squared A, okay? But I know that the maximum acceleration is A omega squared, and the force is M A max. So this would be M times the amplitude times omega squared. So if you want to know the maximum acceleration, A omega squared. If you want to know the maximum force, multiply it by M. Or if you're given K, you can multiply K times the amplitude. Again, the spring constant, assuming the eye acts like a block on a spring, is omega squared M. So These things are found once you know K and omega, phi, whatever you need. This problem, when you do oscillations, and I don't care what it is, it could be like a yo-yo going up and down. It could be anything that's periodic, wheel rolling, anything that has a period to it. If I'd given them the period, okay, instead of the frequency, they would use 2 pi over t. I might have just given them the amplitude. You know, I might have told them that x was a, and in that case, the phi would be 0. Or I could have told them it started at negative a, and therefore the phi would be pi. Okay. Technically, there's a negative sign on these, but it doesn't matter. I don't care whether or not you put the negative sign on the phis. That's why there's a negative sign in. But that's it. That's how you do oscillations. You just are trying to arrive at, again, you want to write this equation. This is the equation. And A is the change of x over t, or it's just given, or given. Omega is either 2 pi over the period, or omega is the square root of k over m, or omega is 2 pi f. And then finally, phi is 0, pi half, or pi if x at t is equal to 0 is a, 0, or negative a. Once you have that, you can then write b and a of t, okay? And that is negative 1 squared sine. And so I could ask you, once you have this equation, I could ask you, what is the velocity at 5 seconds? Since you know this, this, and this, you would just plug in 5 seconds for t. Make sure you're in radians. I can ask you what the I could ask you what the acceleration is at 5 seconds. I could ask you what the energy, now it's not on there, but the energy is Ka squared over 2. This is the maximum energy at all times. So I could ask you for the maximum energy. And really, that's all there is to this. I could ask you for the maximum velocity. The maximum velocity is this. The maximum acceleration is this. The force maximum is ma omega squared. So it really just boils down to being able to figure out what your amplitude, your omega, and your phi is. If you're stuck and you can't find one of them, just tell me. I'm going to use 1 for the amplitude. I don't know what the amplitude is. Or I'm going to use 1 for omega. I don't know how to find omega. Or I'm going to assume that phi is 0, even though maybe it's not. But your goal is just to be able to find the coefficients that go in the oscillation equation. That's it. All right. Got a little time left. I want to talk a little bit about gravity, and then I'm going to come back to pendulums. And the reason why I want to do pendulums last is they have the one weird thing on. All right, so we've been using for weight, or otherwise known as the force of gravity, we've been using m times g, where g is 9.8 meters per second squared. But that's not actually correct. What is actually correct is the force of gravity, according to Newton, is g times your mass times whatever's causing the gravity over r squared. So if you're standing, say, on the earth, your weight is due to, if I rewrite this, this is your mass, this little m, and this g, m of g over r squared, this is actually what we've been calling g. G is 6.67 times 10 to the minus 11. That's the gravitational constant. mg, that g, get rid of it. But that g is just there to signify this big M is what is causing gravity. So what's causing gravity to act on you is the Earth. Okay, so in that case, it would be 5.98 times 10 to the 24th kilograms. R is the distance from your center of mass to the center of mass of whatever causing gravity. If you're at the surface of the Earth, that's the radius of the Earth, which is 6.37 times 10 to the 6 meters. If I plug all these things in, I find out I get 9.8-ish meters per second squared. And my mass is maybe 70 kilograms, so I would get about 700 would be the force of gravity. But as you go higher up, you have to continue. So if you wanted to go a mile high in the air, this radius up here is 1609 for a mile, plus the radius of the Earth. You always have to count your radius from the center of mass to the other center of mass. Okay, so if I had two objects in space separated by r, well, the forces would be gmm over r squared. Third law of pair, they both get the same force. That also means, so if we say the atmosphere is 2 times 10 to the 5th, our radius in this case would be this plus 2 times 10 to the 5th. You would have to count all of it, which is why it's 9.22. So just be careful, make sure that you understand. This equation is really easy, but you got to use it a few times. The second thing is the energy in gravity. We used to write mv squared over 2 plus mgh, but because g is no longer constant, we have to rewrite the energy as, at any point, as mv squared over 2 minus g little m big M over r. These little m's are, say, a ball. If I throw a ball upward, right? Throw a ball. This little m is the mass of the ball. The big M is the mass of the Earth in this case, right? So I'm going to leave that like that. And I want to throw a ball from the surface of the Earth up until it reaches maximum height. Well, if I set the energy, so the energy at surface has to be equal to the energy at the top of its flight, right? So this is the energy at the surface. At the top, something funny is going to happen. I'm going to assume that it gets so far away that r is essentially infinity. So add infinity. So I want to know, how hard do I have to throw a ball so it completely disappears from the Earth? It gets away from the Earth. At its furthest point, v will also be 0. So this will be 0 and this will be 0. And so this whole side of the equation is 0. I can then write m of the ball, v squared over 2, where this is the initial velocity, moves that over, is g m of the ball, mass of the Earth, over r initial. R initial here is the surface of the Earth, so it's the radius of the Earth. And what I see is my m's cancel, and I get v squared is 2gm over r. But this, actually, it turns out, works for anything. This is called the escape speed. If you go that fast, you will leave the planet forever, or the sun, or whatever it is. So, right, v escape is 2gmr, mass of the planet, or whatever it is, where g is 6.67 times 10 to the minus 11. And r is your initial position. So if I look at this problem, we say the sun has a mass of 2 times 10 to the 30th and a radius of 7 times 10 to the 8th. What's the escape velocity of the sun? 2, 6.67 times 10 to the minus 11, 2 times 10 to the 30th over the radius of the sun. take the square root, and you get about 600,000 meters per second. The reason why the sun holds on to hydrogen and the Earth doesn't, you might think it does, but the Earth doesn't really hold on to hydrogen, is that the sun's escape velocity, to get away from the sun, you would have to go almost 600,000 miles per hour or meters per second. Sorry. That's really fast. And you could calculate it for any object that I give you, the radius and the mass. All right. The reason why the moon has no atmosphere is the escape velocity of the moon is very small. It's like 1,000 or something. And on average, particles go faster. The last thing is, and this one I wouldn't worry too much about, but you can compute if, let's say, you wanted to move between 2 points, radius 1 and radius 2. The acceleration of gravity at both of these points would be gm over r squared, gm over r squared. So the change of the acceleration would be gm 1 over r final squared minus 1 over r initial squared. And what I had them do here was I had them compute the difference between their head and their feet if they were standing on the sun versus standing on a black hole. And it turns out that a black hole would rip you apart. The difference between the gravity at your head and your feet, even on the sun, is only 2 times 10 to the minus 6. The gravity of a black hole, the acceleration of gravity of a black hole, is about 15,000 meters per second squared. It would rip you apart. So I think that's cool. So really the only thing you need to remember is escape velocity and force of gravity is g m over r squared, where the acceleration of gravity is g m. Where big M is what is causing the gravity, and r is the distance from the center mass of what's causing gravity to your center mass, where you are little m. And that's really all I want you to do. All right, so the final thing. Physical pendulums. So when we have a physical pendulum, I'm going to use a simple pendulum to start. This is a mass m along a rope of length L. We pull it to some angle and we let it go, and it goes back and forth. And this is one period. And all we want is we want to find the period. How we do this is if we look at the torque on this mass, we know it has a weight down, and it has, at a distance r, it also has a tension. Now, a torque is r cross f. And if we try to cross r and t, we get nothing. But if we try to cross r with mg and the angle between them, and we take the small angle, turns out that what we get is that the torque is mgr times the angle between them. And torque is equal to I alpha. So essentially, I went over this in class, so I'm not really going over this too much. Essentially, what we find is if we divide this by I on both sides, we can equate this to omega squared. And because t is 2 pi over omega, therefore t squared is 4 pi squared over omega squared. Or better yet, I don't even want to do that. I can write that omega is the square root of mgr over I. This is 2 pi times I over mgr. What is r? R is the distance, it's called the radius of gyration, from the axis to the center of mass. So we have a couple cases that you need to understand. The first one, just to help you understand this, that you should know, is the so-called simple point mass. So if we just have like a rock on the end of a string that we're using as a pendulum, I for a point mass rotating around, this is a point mass, this is our axis of rotation, it's going to go back and forth, right? I for a point mass is mr squared. The radius of gyration is the distance axis to COM. So we go from here to here. Well, that distance is L, and R is the distance from the axis to where the center mass is. So R is L in both cases here. If I plug these in, what I get is I get for a simple pendulum or a point mass, I get ML squared. R is L, right? That's how far away it is. Oh, go ahead.
What's up? It's just I got done with class, so I didn't have to have a meeting with her.
Okay.
So I'm good.
2 pi L over G, right? Because our M's cancel and one of our L's cancels. So that's pretty easy, right? Or at least it looks pretty easy. And generally in introductory physics, they just teach you this equation. But we don't have to use a point mass. We could actually use anything we want as a pendulum. So let's imagine, okay, we make a rod. And so you take a rod, like a meter stick, you hold a meter stick at one end and you let it swing back and forth like a pendulum. You may not remember this, but the moment of inertia about a center for a rod, a uniform rod, is ml squared over 12. We can't be at the center though, because there would be no torque. So this wouldn't work like a pendulum if we were about its center. We have to be off center. So if we want to move this axis of rotation to say here, which is a distance d away, we use the parallel axis theorem. And that says that the center of mass, moment of inertia, plus m times however far, I'm sorry, I can't write today, guys, m times d squared, how far we move from the center of mass to the new axis. As long as they're parallel, we're good. So for a rod, ml squared over 12, and then we move it L to the half. So this is L to the half squared, or L squared over 4, right? L squared over 4, because we moved it there. If I multiply this by 3 over 3 so that I can have common denominators, I see this would be 4/12 ml squared, or I for a rod, one end, was ml squared over 3. Now, if I look at the period, I know that I is ml squared over 3, mg, and then r. So my radius of gyration, so my center of mass is at the center of the rod, the axis to the center of mass is L to the half. R is L to the half for a rod. Plugging that in, the m's cancel, one of my l's cancels, and I get the following. 2L over 3G. And then I could plug numbers in. I don't care what the numbers are. But I found my period. Now, let's do another one. What if I have a rod about one end, but I add a point mass to the center of the rod? Well, I's, so moments of inertia of the rod and I of the mass, they just add together to be the total. We already found that I of the rod was ml squared over 3. And we know that this is mr squared, but r is L to the half for the point mass. This is the rod, and this would be the point mass. So for the point mass, this would be L squared over 2 squared, right? Because a point mass is mr squared, and r for the point mass is L to the half. So I'd have these two things. I just add them together. Their center of mass is at L to the half. So my radius of gyration is L to the half. And what I would get is T is 2 pi over M of the rod, L of the rod squared over 2, plus M of the point mass, L squared over 4, over M of the rod plus M of the point mass times G, their total mass of the whole system, times L to the half, which is my radius of gyration. It gets a little complicated, but you can do it. Let's do this one. You know that a solid sphere, okay, solid sphere is 2/5 M radius of the sphere squared. You should know that, it'll be on there. But I could make, let's say I could attach a little hook at the top of the sphere and let it swing back and forth, right? So I'm just holding it like a Christmas ornament and letting the Christmas ornament swing back and forth. Better yet, let's do this instead. I'm going to have a solid sphere that I attach to a rope. So this is a solid sphere. And that rope is going to be where my axis is. So this distance I'm going to call big R, the distance from the axis to the center of the sphere. The sphere has a little radius R. Now, my IP, I have to use the parallel axis theorem because it's rotating. This moment of inertia is about the center of the sphere. I need it about that axis. So I get 2/5 mr squared plus md squared. But d in this case is the distance from the center to the axis, which is r. So I get mr squared. Okay. And my radius of gyration goes from here to the center of the sphere, so also r. And so what I get is I get the period is 2 pi 2/5 m little r squared plus m big R squared over mg big R squared. Now, what's kind of cool about this for a solid sphere is if little r, if the radius of the solid sphere is very, very small compared to the string length, this term would go away and I would get, the m's would cancel and I would get 2 pi times the length of the string over g, which is a simple pendulum, which is kind of cool. So you could do all sorts of stuff. The main idea here is that you have to be able to find the moment of inertia. For instance, I've done this one. Okay. Imagine, and we'll do this in a minute, but imagine you have a massless rod. So the rod has no mass, but I have a point mass at r to the half or L to the half, and then I have another point mass at L. The moment of inertia of a point mass is mr squared. For the first one, if these two both have the same m, the moment of inertia of a thin rod with two masses on it rotating about this axis, I for the first one would be m times L squared over 4, so mr squared where r is L to the half. I for the second one would be ml squared, right? Because r for the second one is L squared. Where is their center of mass? Right in the middle of those two, because they're equal masses. And this would be at L to the 3/4. Okay, so radius of gyration would be 3/4 L. And what I would get is the period is 2 pi m L squared over 4 plus m L squared over mg, two of them, times 3/4 L. Now I would probably do the algebra to reduce that down, but you don't have to. You could just plug numbers into your calculator at that point. Let's say L is 1 and M is 1. So what would I get on the top? I would get 1 times 1 squared over 4. So I get 1/4 plus 1 times 1, so plus 1, divided by 2 times 1 times 9.8, so 2 times 9.8 times 3/4 times 1. If L and M are 1, let L and M be 1. And then I take the square root of that answer and I multiply it by 2 times pi. I get about 1.83. So the period would be 1.83 seconds. The last thing I'll say, and then we'll do this problem real fast that's given, is, let's say for a simple pendulum, T is 2 pi L over G. If I gave you L and I gave you T, you could find G, right? So let's say I told you L was 1 meter and T was 2 seconds. What is G? Square everything. T squared, 4 pi squared, L over G. Multiply both sides by G and divide both sides by T squared. So I would get 4 pi squared times 1 over 2 squared. This is 4. The 1's cancel, the 4's cancel, so I'll get pi squared. And those of you that don't know, what is pi squared? 9.87 meters per second squared. So if T is 2 seconds and L is 1 meter, you get around 9.87 G. All right, so let's do this pendulum. So here we have a physical pendulum is 2 kilograms and 0.8 meters. It's suspended by one end, and a 2 kilogram mass is added at the center of the rod. We've already done this example, but let's do it again. So here's our axis. We add a rod. Okay. Now that rod by itself has a moment of inertia about that end of ml squared over 3. It'll be about an hour afterwards, Ben, the recording. Now, if I add a point mass at L to the half, then I of the point mass is I for the point mass. So this was the rod. And I of the point mass is ml squared over 4, right? Mr squared for the point mass. Their center of mass is going to be at the center of the rod plus the point mass. So their mass is 2, or I shouldn't say 2, I should really say the point mass plus the rod. Their radius of gyration goes from the axis to the center of mass, but the center of mass is at the center of the rod, so that's L to the half. And therefore I can write T is 2 pi square root of I, which is mass of the rod times L squared over 3, plus mass of the point times L squared over 4, divided by mass of the rod plus mass of the point times G times L to the half. And you were given the mass of the rod is 2, the length of the rod is 0.8, and the mass is 2. So MR and MP are both 2. So this would be 2 times 0.8 squared over 3 plus 2 times 0.8 squared over 4 on the top. So 2 over 3 plus half times 0.8 times 0.8. This is 0.747. The top. On the bottom, this is 2 plus 2, so that's about 4 times 9.8. So 4 times 9.8 times 0.8 divided by 2. So this is 15.68. And if I divide those two things, 0.747 divided by that, and then take the square root, and then multiply by 2 times pi, I get 1.37 seconds. Okay, so the first thing I had them find was the moment of inertia of the rod, ml squared over 3. Moment of inertia of the point mass, mr squared, where r is L to the half. Then I had to find the radius of gyration, access to the center of mass of the whole system, which is L to the half. I will tell them. So I said it's added at the center. I guess I didn't really tell them. And then I had them find G if the period was 1.3 seconds. So instead of finding this, I had them find G is 4 pi squared L. Oh, sorry, 4 pi squared. So G is, let me do this the long way for a second. G squared is 4 pi squared. All this I total over 2mg over r gyration. So G is 4 pi squared I total over the two masses times the radius of gyration was L to the half times T squared. Or this was m of the rod, L squared over 3 plus m of the point, L squared over 4. That's what this I total is. And T was 1.3. So plugging all that junk in, you get 10.9 meters per second squared. The real problem is trying to know your moments of inertia. So a few common ones, a disk about its center of mass, these are all center of mass, is mr squared over 2. That's also a cylinder rotating through its center. A point mass or a hoop is mr squared. A solid sphere, and you'll be given these, whichever ones you need. Solid sphere is 2/5 mr squared. Hollow sphere is 2/3 mr squared. You might remember these from torque when we did torque. A rod through the center would be ml squared over 12. And then using the parallel axis theorem, just remember IP is m, I have the center mass, plus mr squared, md squared, where d goes from COM to axis. And so how I just remember the rod about one end, because we know the rod about one end would be ml squared over 12 for the center mass, but we're moving it where d is equal to L to the half. So plus m, L to the half squared is L squared over 4. Changing these, 3 over 3 becomes 3/12. 4/12 is a third. So ml squared over 3 for rod about one end. But really, you could use any of these. I could use a disc. You know, I could take a plate, imagine a kitchen plate or a paper plate, cut a little tiny hole and put a nail through it and let it swing back and forth. The moment of inertia of this, about its center, would be mr squared over 2. But I move from the center up a distance r to the edge, so plus mr squared. So for a plate or a disc through an edge, it would be 3/2 mr squared, right? So on the pendulum, you have to remember it is the moment of inertia, and usually you have to use the parallel axis theorem. mg, do not forget this is the total mass of the whole thing if there's more than one thing. And the radius of gyration, which is the distance from the axis to the center of mass. And that usually seems pretty straightforward, like on a point mass, okay? So point mass at a distance L from an axis, I of a point mass is mr squared, which means it's ml squared. The radius of gyration is the distance from the axis to there, which is L. So T is 2 pi ml squared over mgl, which I want you to all remember for the rest of your life. The reason why it's L over G is because the moment of inertia of a point mass is ml squared, and the radius of gyration is L. So if you can do that for some simple objects, it's not going to be crazy. It'll be pretty straightforward, hopefully. Anyway, that is everything in depth on here. If anyone has any questions, I'm open to answering them. If not, we can get out of here. And hopefully you'll all feel okay. Remember, you get 2 sheets, front and back, like normal. And just do your best. Hopefully it won't be too bad. Hopefully all your finals are great. Thanks, Ben. I'm going to record this, or I recorded this, so I'm going to wait for it to compile. It may show up automatically, but I'm going to check it before I leave. I have a final at 1 on campus for 2510, and I'll make sure it's up before I leave. So hopefully by noon, this will be up. Yeah, no problem. I kind of went over all this on Friday too. So this is just more stuff. For those of you who are here, do not go crazy if you have other finals. Just make sure you know this test. And I mean, there's more than enough stuff for you to cover on this test. It'll be 4 questions, so you'll have about half an hour. We have 2 hours. You'll have about half an hour for each question. And remember, I'm not trying to trick you. I prefer straightforward, just asking you for things. So if you find yourself kind of going off into the weeds, you know, and trying to study like all sorts of stuff like Pascal's or whatever, don't. Just make sure you know Bernoulli's equation and the continuity equation. Make sure you know, and the reason why I do this way, make sure you know these for Kepler. These are the equations that you need to know. And for Bernoulli's, these are the equations, but you also have to know that when it's open to the air, the pressure is an atmosphere. This is the relatively simple pendulum equation, although you have to know how to use the parallel axis theorem, and you need to know what R is in that case. For oscillations, this is the equation, but you can find A and omega and phi from those things. It's a few other little things to know, but they're mostly plug and chug. And gravity, force of gravity is mg, little m, and the escape speed. So there's really not a whole lot you need to make sure you know how to do. And you have more than enough room for notes, I think. Ben had asked me if I would open up homework 11. Homework 11's open, that's chapter 15, till Thursday. Although technically I don't think I can open it past Thursday. I don't know for sure though. But anyway, other than that, I'll see you guys at 9 on Thursday if no one has anything they want from me. See you all.
Professor, when are you posting for the notes in the review on the final one?
Oh,
When on the
no,
notes that we already been reviewing on it?
I didn't post any notes. It's just this. If you want to know where this is.
On the lecture, I mean the lecture. So just watching knowing like.
Yeah, I didn't post any notes. I just posted this solution right here. And then this
I don't know the one that you already reviewing on the whole the 3 chapters of thing, like chapter 13, chapter 14, and chapter 15.
That was this. That was just
on the PowerPoints. On the PowerPoints.
Yeah, they're all here. 14's there. 13. Oh, they're not here, huh? 13's here. Oh, 15's here, 13's here, and 14's there. So they're all there, Ben.
Can you also like sending for the like the PowerPoint, so I just gonna be like looking on it to for the revision and then just trying to learning on it. So
I,
it's just
I
easier for me like to looking the whole everything about it. So just
yeah,
easier
they're
just send it
that's what
on the
these are though,
PowerPoint.
Ben, right? These are the notes. If they'll open. Anyway. So these are our notes. And they're pretty short. Is that what you meant?
No, it's just meant not for the PowerPoint on it. The one that you already writing about
Oh, this.
reviewing.
Oh,
Yeah,
this.
yeah, 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 yeah,
Um,
yeah, yeah. I
so
mean
in
this
it,
one, yeah.
and then yeah, I can save this and upload it right now. Let me do that for you.
Okay, thank you, Professor. I just was trying to like can looking on that PowerPoint and then just can
Yeah. So this
reviewing
is
for myself too.
it's a little messy though, but I mean, if you want to review,
That's okay.
um,
Yeah, I just
I'm
cannot
sorry,
be learning
I
on it.
wasn't planning on posting it, so it's a little gross, but I feel bad, but anyway, yeah, this will be this video will be up. Um,
On the canvas too, right? Canvas?
yeah, it'll be up in about an hour, just so you know. Where did you just?
Is it on the canvas, right? Or is it on the YouTube something? YouTube?
It'll. I'll post a link in a announcement. Um, so it should be. You should just be able to look in the announcement in like an hour, and it should be there.
I
So,
see.
and then this is the review that I just did. So, yep, you should be all good, hopefully.
Okay. Okay, thank you, Professor. I think it will be good for me, like just for reviewing
I
for
think you'll
whole the
be.
whole thing, you know, for
Yeah,
whole
just
thing
make
for
sure you know how to
Thursday.
do this
Just
test,
fun.
Ben. Just make sure that you know how to do the sample test, okay? And you'll
Okay,
be.
I just trying to getting reviewing, like doing the song practice
Yeah,
the one. That's all.
don't go
That's
too
all.
crazy. Uh, just do it in chunks, little chunks. Um, all right. I'll see you soon. I'll talk to you later.
Okay, see you, Professor. I'll see you, Professor.
Stop share.